My name is Philip Judge. I'm obviously English, and I would like to talk to you today about our Sun, the mercurial star at the heart of our solar system. My goal here is to review the Sun's history from a planetary perspective. A planetary perspective is shown in the figure on the left. It reveals humanity at a sunset with planets illuminated, with our sky illuminated, and it also shows our technology in space. The International Space Station is somewhere in that figure. So I'd like to talk to you about the zero-age main sequence sun to the present day and beyond. I'm going to briefly put it in a galactic and stellar context. The stellar will be very important later. There will be some mention of planetary connections, but this is far too complicated for me to discuss. There is a leitmotif here, and that is that the combination of a convective star and a rotating star always leads to a magnetic machine, generating fast fluctuations and emissions of particles and photons and magnetic fields with energies far above the surface energies. One example of the mercurial nature, the peculiar nature of the Sun, is that it possesses a corona. And here's a beautiful picture from Eclipse 2017. And this is in fact an example of the solar machine in action. So in a galactic context, we can see that the Sun lives in a spiral arm. It's a type population 1 star. Existence of uranium on Earth from supernovae is showing that it's been exposed to neutrons, the supernova, and that this generates core heat, and the core heat, as we'll see, generates magnetism, which is important for life on Earth, actually. The Sun does not belong to a particular stellar group. It is similar to stars in M67. There are such things as solar twins, and there are a couple of them. And one can see from the luminosity function that the Sun is a fairly typical star lying in the metal-rich spiral arm of a pretty typical galaxy. Curiously, solar twins are surprisingly rare, depending on your selection criteria. The figure on the left shows an HR diagram, and it positions Sun-like stars on the graph together with the Sun itself. And you can see that there's just a handful there. Of course, there are many billions of stars in the galaxy, but finding ones that are precisely like the Sun is going to be very difficult, as shown on the right-hand side, where I've taken from Wikipedia, actually, forgive me for that, data for what are called solar twins. And you can see that these are distributed in a kind of random way in these plots. We have relatively poor quality data here in that the typical error bars on the left are rather large, encompassing nearly all the stars. But this by itself shows that we really don't know if the Sun has a genuine twin. But this is after many years of searching, and there are very few stars distributed in these figures that will have identical to within rather small criteria properties to the Sun. But these data are really improving a lot, and one of the things that we will be talking about here is the relationship of the Sun in earlier times to stars through the use of things like Kepler and TESS missions. Now, in the galactic and stellar context, I'm just listing here some parameters for your convenience. It's a middle-aged population 1 star, and the track of a 1 solar mass star is shown on this theoretical HR diagram. Now, the sun's abundances are very typical of this region of the galaxy, unlike, of course, the Earth, which has undergone some significant fractionation, loss of hydrogen, helium, etc. Now, as a function of time then, we can look at the main sequence lifetime. And this is plotted here as a function of age. And what we see is the luminosity in the blue line being about 75% of what it is today at the 0 age main sequence. And we see the effective temperature also shown. It's around 57-75 Kelvin, plus or minus a few. The sun is about 4.6 gigayears old. One of the questions I'll address at the very end is the sun peculiar? This has been talked about a lot in terms of anthropic principles. Namely, is there something funny about the sun that led to life? So far as we can tell, solar stellar astronomers really can't tell if there's something peculiar about it. What does a star built from first principles look like? Well, it's going to look boring, relatively boring. The sun's temperature will, in radiative equilibrium above the convection zone, follow a temperature with optical depth. So as tau increases into the interior and then it decreases out, we end up with the temperature of the outer layer of the star being about the 1/4 power of a half of the effective temperature. It has some limb darkening, which also comes from classical theory, so it gets darker at the edge and in the middle. It will support convection, and here's the surface component of that called granulation. So this will vary a little bit in brightness as these come and go on a period of about 10 minutes. However, in the 1970s, it was discovered, of course, that the sun oscillates and has normal modes of oscillation. This is not surprising. The sun is an elastic fluid. It has stochastic excitation from these granular cells. And so we end up with a pattern on the sun of the linear combination of several thousand modes of oscillation leading to patterns like this on the surface. These are all classical kind of theoretical ideas. It can also support differential rotation. But note that this image is not theoretical, but it was attained by sounding the sun in the 1990s. This behavior contradicted many theoretical ideas of how this would look, and it will be a critical parameter in our story. What you see here are contours. It's like looking at a contour map. Regions of very high rotation near the equator, and regions of very low over near the poles. And you can see that the pattern extends from the surface down towards the interior in a way that's almost radial. And so until it gets to about 0.7, when it becomes more azimuthal, the velocity, the angular velocity. Now, these regions where these contours are steep turn out to be very important for magnetism. So a star built from first principles would have a spectrum roughly like a black body. Not exactly, but you can see some edges as well as an overall shape of a black body. And it's essentially nothing at all below about 1,000 angstrom, about 1/5 of the wavelength of light that we see. The sun does, however, show some truly outrageous behavior. Two of my favorite characters in fiction are shown here. And what kind of behavior is this? We've become accustomed to seeing the sun do some very peculiar things, and many of you might be aware of this kind of a representation of what the sun looks like. One starts at the photosphere, and it goes into the corona, and there's the corona. That's about 1,000,000 degrees. This is the surface of 5,000 degrees, and you see these innocent looking spots on the sun, which are accompanied in the corona by these enormous bright regions in the corona. We're very familiar with this, but why must it behave like this? So I'm going to talk about the remarkable case of global solar magnetism and why you should care. The sun really is a stable nuclear processor, as we know. So from first principles, we would expect global time scales of about 10 to the 5 year for thermal changes, or about 10 to the 9 years, as we saw in the evolutionary plots for nuclear processing. Now, the locally chaotic motions of convection and global oscillations have timescales of minutes or so, and this is perfectly reasonable from the point of view of a first principle star. It's nearly a black body, as we said. It has no significant magnetic or electric fields, but there may be some long-lived turbulent magnetic fields, which people talked about in the 1940s onwards. Instead, what we see are rapid changes and some order from the chaos of the rotation and convection imposed by the rotation on the convection, and it presents us with well-known but unsolved problems. How exactly is a magnetic field that we saw in the coronal image generated on a large scale? How is it dissipated? And what we will talk about are effects of magnetic fields now in terms of a word called activity. Activity just simply means anything related to the magnetism in stars. So here is our fictional star, and here is measurements. Here are measurements of the brightness of radiation, varying between solar maximum and minimum by about a factor of 10 in the ultraviolet. Remember, we see light at the peak of this curve. The Earth's atmosphere sees light at the peak of that curve, but it's also very sensitive to ultraviolet radiation through the molecular components of our atmosphere. And you can see now that the dominant component of our atmosphere at various heights, nitrogen, is dissociated by ultraviolet light. And you can see that from this, the sun's going to affect our atmosphere rather dramatically. Here is a plot showing yearly average sunspot numbers from the beginning of telescopic observations onwards. I've shown various characters here. The top one is William Shakespeare. We have Galileo. Isaac Newton lived during a period where there were very, very few sunspots. This is a real fact. It's not something to do with the weather or telescopes or people's eyes. This is a documented fact. Leonhard Euler is shown around 1750 with some good healthy sunspots, and this is the number of sunspots seen on an average every year on the sun, and it varies by about a factor of 100. There are some days, in fact, when there are no sunspots at all on the sun. Fraunhofer is the next one, around 1800. James Clerk Maxwell. These are all people that play into the story of the sun. And then the next one is with a magnetic notation is, in fact, George Ellery Hale, who discovered the Zeeman effect in the sunspots around 1906. The bottom person is Alf Vane, who will play a role shortly. There's one person here for which I cannot get a picture and actually have the wrong picture, but it shows this little star. This is a chap called Carrington, and in 1850 there was an enormous event which played havoc with magnetism, the Earth's magnetism, to the extent that it was possible to communicate across a continent just by induced electromagnetic fields from variations in the ionosphere. No batteries were needed. Another person, of course, that will enter into this thing is Albert Einstein, and he will be related to Alf Vane shortly. One of the characteristics of the sun that was known early on is that they do arrive in a stochastic fashion in some sense, but there also is order in amongst this chaos. And you can see here, from first principles, there's no way we could have anticipated such behavior. What is this? This is a butterfly diagram drawn by Annie Maunder. It actually hangs in the halls of my institution, High Altitude Observatory in Boulder. And you can see the wings of a butterfly pattern. So the sunspots appear in a time latitude diagram in a very ordered fashion. This is also shown in recent work in which we've actually not measured the sunspots, but the magnetic field. The Zeeman effect is capable of measuring the magnetic field in the sun. Particular lines are very sensitive, and we see here a plot from 1970 something all the way almost to the present day, made by David Hathaway. And the blue and the yellow correspond to opposite polarity magnetic field pointing in our direction. So this is what they call a longitudinal average magnetic field. The patterns in this are remarkable, totally unanticipated. Remember the timescales of which anything thermal or nuclear can happen, hundreds of thousands of years and longer. Here we have a cycle going on in which it repeats every 11 years in plus and minus. The entire magnetic field of the sun, if you look at the top row, changes sign coming out of the North Pole every 11 years, completing a cycle every 22. This is known as the Hale polarity cycle. Now, you can also see very many things, the noisy things in the middle of the sunspots, but you also see this pattern of waves kind of moving towards the poles as time goes on. This is the effect of what we call a surface effect, where one has meridional circulation, a well-known phenomenon in rotating fluids. And it turns out that what we're looking at here are the action of a dynamo, a large-scale dynamo. A dynamo being something that converts kinetic energy of a partly ionized or ionized plasma into a sustained magnetic field. And in this case, it's a global scale magnetic field. The noisy stuff in the middle of the spots, the waves at the edges, are a propagation of spots towards the pole, spot magnetic fields. They are tilted, so you get a preferential sign of stuff going towards the pole. You also get spots migrating, a little bit of migration towards the equator and cancellation at the equator. These are all interesting things that happen, which from first principles could not be identified. Now, even more outrageous is the fact that in the space of about a few tens of minutes, the sun, these sunspots, which host the overlying magnetic fields, can make changes on very, very small time scales. On a few day time scales, this is a wonderful movie showing how the sun evolves around the disk of the sun. It shows the images of the corona. This is also showing gamma rays from an observatory RESI. And then you see subsequently the dumping of an enormous amount of material into interplanetary space. And that noise at the end is not some kind of detector problem that's unrelated. It's directly related to the fact that the sun is a source of high energy particles. Let's do this again. And so what we're seeing here is the sequence of events that happen simply because the sun possesses a magnetic field in a very non-classical way. Again, the gamma rays associated with extremely high energy particles. This has to arise from electric fields involving the changes of magnetic field at the surface somehow, an area of great interest. And then we see the effect in our spacecraft. So why is this outrageous? Well, I'm going to talk for a few minutes about some physics. I'm going to talk about a model, the simplest model of a magnetized plasma, and here are our two characters. Einstein changed Newton's formulation to fit Maxwell's equations, as we know. He got a Nobel Prize, but not for inventing special relativity here. Now, magnetohydrodynamics can be thought of as the reverse applied to a conducting fluid. So we look at the plasma, it's got charges in it that are free to move. The protons are very heavy, they don't move very much. But if we put an electric field across it, the charges will separate and you'll get an electric current flowing. So that's what a conducting fluid is. We change Maxwell's equations, not Newton's equations, to fit Newton's laws of motion, and we take transformations for the fields and the plasma, including to order the velocities in the plasma divided by light speed, to fit Newton's laws of motion. And this chap, Alfvén, looking very pleased with himself, got the Nobel Prize for this and related work. How does this work? And this is hopefully not too frightening, but if you combine essentially Faraday's law with the equations of motions of electrons and protons, including collisions, you can write down not only the equations of motion for the plasma, but also an equation for the coupled magnetic field. There can't be an electric field in the frame of motion of a plasma because the electrons will move very quickly to short that out, except during perhaps very dynamic events like flares. So what is this? We have a plasma, we have electrons and protons and ions, and we have a magnetic field. The plasma has a bulk velocity u, and it has a resistivity or a diffusivity defined by those equations up there. And this describes how the magnetic fields evolve. So this is what we need to describe essentially all the interesting bits in solar physics. Notice that we have a source term, it could be a sink term, which is nonlinear in our equations. Remember, we have to solve, if we were to solve this, we'd solve for u and b. We can't prescribe one or the other, ab initio. And then we have a sink, which simply involves the resistance of the plasma to electrical currents and a del squared of b. Now, if we have a situation where the plasma is not moving, then we end up looking at various phenomena. The outer core of the Earth, the liquid core, can change then in about 10 to the 4 years based on this equation. So it would disappear in about 10 to the 4 years. The Earth is much older than that, so we know it must possess some kind of dynamo. Now the Sun, in principle, if it were left to its own using molecular diffusivities, would lose its magnetism about 10 to the 9 years. However, if we now are clever with this equation and invoke some mathematics involving turbulence, which is a frightening thing, but nevertheless it is doable, then you find a timescale, curiously, of around 3 years. This is now replacing this eta parameter with something derived like an eddy diffusion coefficient, familiar in atmospheric sciences. Okay. And then now, on the other hand, so that's just the decay, that's just the second of those terms. Now, if we really want to generate magnetic fields, I'm going to look at the extreme difference, the extreme other case where it's an ideal fluid. There's no resistance. And one can expand this in the following way. And given a velocity v, and I've changed that from u because I'm going to say, well, I'm going to fix it in my mind, and I can stretch, shear, and compress the magnetic field, and I could change it, the magnetic field, according to these things. And as you can see, the middle term, shear, is something that was present in the interior of the Sun, and that will be very important. In a nutshell, I'm just going to briefly review how the magnetic field is believed to be formed today. You need to break some symmetry, and the way to do that is to use rotation. And differential rotation is not part of that breaking of symmetry, but, well, it is part of that breaking of symmetry, but we see that it's a rather simple process. You start off with, let's say, a dipolar field, north-south, a poloidal field, as it's called. It gets stretched out by the differential rotation. The equator moves faster than the poles, so the magnetic field is pulled. When it's pulled, in the places where it's not parallel, in the places where it's pulled by what's called Lorentz force, the energy of magnetic field is increasing, and you can see that by the number of wraps in frame C. There's a lot more field lines per unit area there. That's the definition of a stronger field. Now, when one has convection, one has an upflowing convection. When one has that on the Earth, you can see you can build a cyclone in a very large, at certain times of the year. And the same kind of idea can be imagined going on in the Sun, because when the convection is moving upwards, the fluid moves in from the sides, u phi and u theta. It's a cyclonic motion, and it generates a twist to the magnetic field. When the magnetic field gets strong enough, the magnetic field will emerge from the interior where it might be generated, and then coupled with some processes that reprocess the opposite polarity fields, you can get magnetic field, which completes the cycle. And what it does is, as you can see, it goes from A to F, and that A to F is a change of magnetic field direction. The entire polarity of the Sun changes. And that happens, excuse me, in the following schematic way, as shown as in the bottom. You have an omega effect, stretching it out. You have an alpha effect. The omega effect converts poloidal field into toroidal field, and vice versa. And this is a cyclic kind of phenomenon. That's the end of my physics interlude. Now we're going to talk about the magnetized Sun in time, and we're going to talk about data acquired of the Sun itself and from the solar system first. As we saw, the history of the Sun's magnetism is recorded to some extent in history by the sunspot record. In this period, we see predominantly the 11 or 22-year magnetic cycle of the Sun, except during two periods, except during one period, the Maunder minimum, and then later a significant reduction in the amplitude of that oscillation around 1800 in the Dalton minimum. These are real minima. These are periods when the sunspots were present, but they were very seriously suppressed. They mostly appeared in one hemisphere in the Maunder minimum. So we have a nice record in history from the beginning of the telescope to show us what the Sun was doing over about 400 years. There are cycles. People have looked for cycles in this thing for periods of anything from 11 years on up. And but this is just too short, really, a time period to specify any of the periods that might be present on a long time scale. But clearly the Sun is modulating its, somehow modulating its magnetic activity, which is very regular, but it's also modulating the amplitude in a rather unpredictable kind of way, according to these data here. Now, there is another way of looking at the solar magnetic variations, and that is by looking at geological records. Now, the Holocene, the past almost 10,000 years, has been a period of relatively stable climate, and that's required because the climate of the Earth affects the kind of geological records that we have. And rather cleverly, people have looked at the variation of nuclear isotopes as recorded in ice cores, as related to modern neutron monitors, calibration through those things. The bottom line, though, is that it is possible to actually go back to about 10,000 years before the present time. And what do we learn from looking at this? This is by modulation of the galactic cosmic rays coming sort of isotropically from wherever they originate in the universe into the solar system, modulated by the large-scale solar magnetic field as it undergoes its evolution. What we see here then in the arrow is the Maunder minimum. So you can see it on the left and you can see it on the right. Now, there are various episodes shown here where the sun was apparently significantly more active. This is a measure of the interplanetary magnetic field strength in nanoteslas. And what one can see here is various episodes going back, say, to around the time of Christ, where the sun was pretty active, and about 7,000 years ago. But there are also periods where it's rather suppressed, and that's marked with these shaded boxes, drawn somewhat arbitrarily. But you can see in the bottom plot, this is a low frequency pass version of this, that there is almost a secular change throughout this period in the dashed line, and there are also little oscillations that appear to be on the order of, 1,000 years or so. So anyway, the sun is again revealing to us its order out of chaos. It's a chaotic system looking at the top figure, but there is overlying order on it. There's some, if you like, memory inside the sun that's controlling these things. Okay. Now, for variations on astronomical timescales, we have to rely on stellar data, actually, and that's what I'm going to talk about for most of the rest of this presentation. There is, of course, a relation between angular momenta of the star itself, the magnetism, and the magnetic activity. So we all know that the stars are endowed with a non-zero angular momentum. Sun-like stars possess convection and differential rotation. That means, according to modern understanding, that we're going to have some kind of large-scale dynamo. On large scales is the important feature here, because when you have an organized magnetic field, say a strong dipole component of the magnetic field that changes sign every 11 years, on much longer time scales, this large-scale magnetic field is also accompanied, because it's hot, by an outflow of material driven by the pressure gradient of the hot material. And so we have a wind emerging from these low-order multipoles of the sun's global magnetic field, which then, when the mass leaves the environment of the sun, it carries with it angular momentum. Therefore, the sun is going to, in a way, spin down. And if we assume that the spin down is more or less uniform across the, say, the convection zone, then we can say that, the sun's outer convection zone is dropping its angular momentum, and we can measure that in different kinds of stars. Now, in recent years, this area has grown. There is a field of research called gyrochronology, which was hinted at in earlier epochs, but because of asteroseismology, what is this? This is the oscillations that we saw for the sun, the global oscillations. We have various missions in hand. One is now past Kepler mission. There are various other efforts made on the ground using different techniques, but these measurements of brightness oscillations in space using photometry have vastly improved our understanding of stellar ages and rotation rates. The rotation rates are very clear, because you just look for a period of a month or two or three, and that suffices to identify the passage of spots on sun-like stars, for instance. The stellar ages come from probing the properties of the interior of the star, and a formal inversion problem is performed to understand how the age relates to things like the internal structure, the composition, etc., as the star evolves. Empirically, we see some very interesting relationships, starting with a paper in '72 by Andrew Skumanich, who showed that there is a relationship between stellar age, chromospheric activity, and therefore magnetism. This is a very interesting paper by Noyes et al. In 1984. What we see here is a plot, the actual scales don't really matter on either plot for our purposes. The left one, the vertical axis, shows chromospheric activity, so that's the strong magnetic field, and on the x-axis one sees a quantity called the Rossby number, familiar to some of you, in which basically as you move from left to right in the figure, it goes from the strong inertial effects of rotation on the stars to weak rotation. And what you see is essentially, as measured from the ground in these calcium H and K lines, that's what the y-axis measures, one sees that the fraction of radiation coming out in these activity sensitive lines that are measured from the ground near 4,000 angstrom, it decreases with this parameter, the rotation parameter. And actually, many of these, for a given spectral type, the convective turnover time on the denominator of the abscissa is sort of fixed. So this is also an age diagram. So one sees that the amount of magnetic activity decreases with time. Again, this is a kind of order from the chaos of the convection zones of stars, imposed by the rotation and presumably differential rotation. In fact, this is so good that this business of gyrochronology, namely fixing the age of a star by its rotation rate, and also estimating the rotation rate by the Kepler data on short times, but also using the age parameters from the inversion, one can calibrate this thing. And in fact, here is a plot early on from Maibaum et al. And you can see what's plotted is on the sort of x-axis is a mass plot, so the sun lies upon that line shown. The y-axis is the age of the stars as determined with these various techniques, and then you have a rotation period. And what we see is this is a single-valued plane in this three-dimensional space, allowing you, say, if you know the mass, then you know the relationship between age and rotation. And various calibration efforts have been put in, also to include the known classical open clusters stars, such as the Hyades on the right. This is a very similar plot, now plotted with the inverted, not only the age, but also the effective temperature of the star, and the sun is shown together with many other stars. As you can see, they belong, the sort of lines in the plot go along with a cluster, etc. So this stuff is really opening up the classical HR diagram kind of approach to really show us with these modern instruments how the sun can be placed in a context. Now, over many years, people have monitored this activity, this calcium line near 4,000 angstrom. And I've taken this from work from Ricky Egeland, his thesis in 2019. And what one sees are various sun-like stars showing different behavior. Now, these are not offset arbitrarily. This is actually the strength of the activity in the star. So the top one is very bright in this line and very strong. And as we drop down, we see different kinds of behavior. The bright stars tend to be erratic, with some sign of periodicity sometimes. Then the intermediate stars also can be erratic. The sun is shown as measured with clever instrumentation to measure both the sun and the stars with the same instrument, so we don't have any intercalibration problems in the same way. And then you have a very inactive star shown at the very bottom. The sun shows cycling. it shows a very unusual cycle, as we'll see. About a third to a half of all stars tend to cycle in this fashion. This is a picture, in fact, of the sun in time. So let's look at the young sun from the point of view of solar type mass stars, and look at the evolution in time. So what are we looking at here? This is in fact regions of so the ultraviolet on the right hand side extending down to soft X-rays in sort of the peak of this plot on the left hand side. So the UV changes a little bit. The UV tends to be brighter in the red. It tends to be dimmer down in the blue stars. So as a function of age then, we have a kind of chronology here of what we expect a star like the sun to do, including one older than the sun, as a function of time in these X-rays. And we don't show the ultraviolet yet. That's coming in a moment. So what is this showing us? Remember that 100 angstrom corresponds to 100 electron volts. That's a good in energy. That's a good thing to remember. So that means that 10 angstrom is 1,000 electron volts. This is 10 to the 4. Okay? So this number here is about what X-ray satellites, soft X-rays, look like, measure in the sky. So at about this energy, this is typically characteristic. Notice the scale. It's a logarithmic scale, 4 orders of magnitude. This is no small change as a result of the evolution of a sun-like star. If we go to the ultraviolet, we see these same stars shown in a plot like this. This happens to be very strong lines of lithium-like oxygen-6. It doesn't really matter what they are. Some lines of carbon. What is interesting also is the continuum. So this is a continuum formed by emission and absorption of radiation, say in the carbon photoionization, resulting from the photoionization of neutral carbon. And what one sees again is the enormous difference between at least an order of magnitude, maybe even bigger, for these young stars. It's not 4 orders of magnitude, it's an order of magnitude or 2. So one sees that the ultraviolet increases a bit and the X-rays increase a lot, and that's very characteristic of what we see as the sun in time. Now, if we now plot the period in days, which as we saw from the previous plot, maps out to ages of the stars, and 10 days is about 1 gigayear, so this is a youngish sun, and here is the older sun somewhere in here. What we see then is, if we look at the X-ray luminosity, we see almost 4 orders of magnitude difference at around 1 to 2 keV compared with the sun today. So the early solar system, 100 megayears, was flooded with X radiation. The other thing I want to point out is that it doesn't continue on the slope for older stars, it saturates. So there is some feedback of the magnetic field on the dynamo, this is the hypothesis, or when the sun was very young, to stop it becoming just a non-linear, sort of a linear growth of activity as a function of the dynamo parameters, namely the Rossby number. Okay, now if we go to now on a different kind of way of looking at this, we just put it into various bands, and what do we see? Well, the sun is fixed at 4.5 gigayears, and we see that number is 1. As we go a little bit older, the sun drops just a tiny amount. In these remember, this is the high energy tail. The spectra of the visible sun look pretty similar for these things, the visible stars. So this is the high energy tail, and in the soft to hard X-ray region, the slope is very steep, such that you have almost 4 orders of magnitude change between a 0.1 and 10 gigayear old star. And the others are, as you go progressively softer in energy, so lower and lower energies, longer and longer wavelengths, get smaller and smaller. Now let's have a quick look then at the kind of effects that one might have expected in the early solar system. Now, this is the task of other people to talk at this meeting. I'm just going to point out what is which is what I think a very nice paper here by Lama and colleagues a couple of years ago. And this is a plot I've taken from them. It can be a little confusing, but it is relating both the Earth and and Mars to this extreme ultraviolet change. So this is maybe around 100 electron volts, 100 angstrom. This can photoionize, photodissociate gases in the atmospheres of the star, of the planets, comets, you name it. Okay, so what we're looking at here is they've got plotted three kinds of rotators. Well, what does this mean? It means that it's this star here is presumably one. They have the same kind of age, but it started off with a much larger rotation rate, or it didn't lose as much angular momentum as this star and this star. But the point here is a qualitative thing. So what I'm going to point out is that simply that one goes from about photonization, photodissociation of the atmospheres of these planets, 2, 3, 4, about a ratio of about 400 by the time one reaches the Earth current date. So this is what the sun's one of its major influences on the planets. Don't forget also that there is a solar wind. We don't know very well how much that actually alters and affects the planets, but there are these things called CMEs. Remember the movie showing the blowing up of a huge sort of light bulb shaped thing on the right hand side of the sun? That is a coronal mass ejection. What it is it's as a result of a changing topology of the magnetic field driven by magnetic field evolution at the surface. It blows off a whole parcel of massive amounts of plasma tied into the magnetic field that flows throughout the solar system and can light up various things on its way, such as the Earth, generating enormous perturbations to our ionosphere and to our technical infrastructure. So this is another one from Wikipedia, just showing the various periods on the Earth that we've been talking about, and or that other people will be talking about, showing that the smallest this is a linear scale in a clockwork direction of age, and so if it was a minute it would be 1/60th, so it would be about 100 million years. So very poor resolution, and that's why the first humans appear at the very last moment in time. But anyway, let's just summarize some of these things here in this plot. So this is a sort of simplified version of that, showing the same plot of the evolution of the sun. But the remarkable thing is, of course, that these events, I've just marked them from the previous plot onto this one, showing you that the first life originated really a long time ago, at a time when the Earth was actually rather dim. The other thing that I want to point out here is that we'll anticipate a result coming up in a moment. There is going to be no more magnetic spin down. This is a fairly recent result in the last 5 years from Kepler, from gyrochronology. The stars they've looked at tend not to spin down anymore. So it's just in this first 4 to 5 billion years that the sun-like stars will spin down. Okay. Another result from Kepler, of course, is the fact that they keep observing these things continuously for some months. And so you can measure flares, and the relationship between solar flares and stellar flares is something that people have looked at for a long time. There are things called flare stars in dwarf M stars. We're not talking about those, we're talking about one solar mass stars. Even those can have super flares, and here is hard evidence from Japanese group showing that a Kepler super flare occurs about once every 440 years. That's as a result of integrating this kind of distribution shown on the right. Now, the sun lives somewhere in here at its strongest. The Carrington event that changed the ionosphere to the extent that you could communicate over many thousands of miles without putting a battery on things over the telegraph system is about here. Most solar flares, a really powerful solar flare lives here. But look at this. The stars annotated with a distribution of these stars with age is not known in this figure, but if you're a 1 gigayear-old star or older, you get flares that look like this distribution here. So one can end up with a factor of 50, 500, 5,000 times the amount of energy from that flare that disrupted our Earth's magnetosphere 150 years ago or so. So one of the consequences of this is that while we don't believe something like a superflare could have, destroyed, removed the large dinosaurs, we don't discuss this option very much anymore for various reasons. The potential for damaging life here is significant, and I'm not going to talk about that because it's not part of my speciality. Okay, so there is such a thing that people talk about, the faint young sun paradox. It's crossed out because I don't think it's a paradox anymore, and I don't believe it's an astronomical problem, such as, well, when the sun was younger, it had a higher, stronger wind, therefore it lost mass, and it was a more massive star early on than it is today, and therefore it would have warmed the planet more. Now that, I think, has been ruled out to the best of some clever people's ideas of how to measure the mass loss rates of these stars. It's not easy at all, and involves pretty much extrapolation of what we expect on the basis of the Earth, of the solar system, I beg your pardon. Okay, so what are we looking at here? Well, here in red is the solar luminosity as a function of date before the present date, and here we're looking at 70% or so, 75% of the amount of power hitting the Earth's disk from the sun, the radiant energy. And the solution proposed by various people now is that the problem was that we had water, evidence of water down many billions of years ago already, liquid water on the surface. Remember, we need plate tectonics, we need magnetic fields, and we need surface interactions between rocks and liquid water. That's our understanding of forming life, both in the bottom of the ocean and at the surface under sunlight. And so, what we're looking at here is a proposed solution based upon the fact that we think the Earth's atmosphere, without really behaving as dramatically as Mars, whose atmosphere was stripped, or Venus, whose atmosphere was catastrophically heated, was able to sustain a temperature convenient to the formation of life over a long, long period. And I find this to be, a very intriguing fact about the Earth and the Sun and their joint evolution. And I'm interested in hearing what other people might have to say about related things in this meeting. Now, as we go to the old Sun, we can look for stars that are young, 1 gigayear and less. They all correlate very nicely. They drop down towards the Sun's age. There is, of course, scatter here, which is not surprising. These are not a homogeneous set of objects that we're looking at in the same direction at the same equator place all the time. There's various things that could produce this kind of dispersion that you'd expect naturally. But what happens is that as you go to a rotation period of about that of the Sun, suddenly all you end up with is a scatter plot here with no correlation. They're absent up here because they're not spinning. There's not a lot of activity for those things, but there's a minimum amount of activity that's more or less kept going up to a considerably older kind of star. Another way of looking at this is to look at the age as determined from astroseismology on the x-axis, and its measured rotation as determined from classical fluctuations and time series analysis on short periods. Again, we see the tight correlations here until we get to this point, and now suddenly these stars are all kind of rotating similarly, even though they've evolved through another 2 to 3 billion years. What this means is that it answers actually an old interesting question from the days of Rosat, 1996, which shows that pretty much stars have X-rays in the local solar neighborhood. This is not an instrument detectability issue, but these stars have a lower limit. You don't find stars without X-rays. And this would be consistent with the idea that a large-scale dynamo still operating, if you have a sun at this age, it's not going to look very different from a sun at this age, and you're going to have X-rays in old age. Okay, now finally I want to talk about is the sun a peculiar one, a peculiar star? Well, yes and no. Mostly no. One of the things you have to remember is that we only see it equator on. This is not often really appreciated, but you can remember from those magnetic diagrams, in particular, if one were to look at the pole of the sun, you would see a very smooth change from one polarity to the next. Whereas if you look at the equator, you see all these noisy sunspots. So we have to remember that. Now, there is one way in which the sun appears to be statistically rather unusual, and that is that Ricky Egeland found that in his thesis that the cycling behavior is the most regular. It's the cleanest, if you like. It has the best, purest tone, if you were to hear this oscillation of all of all stars, and it's very similar to the K stars, not the G stars. The K stars, of course, have a lower mass but a much deeper convection zone. So I find that intriguing. Photometry seems less variable. In other words, the sun is a little bit under variable, considering its age and amount of calcium activity. The brightness in broadband measurements seems to be less variable. But there is an interesting proposition by Radek et al., which is that the sunspots make the sun dark, but the decay of sunspots make it bright. This is a feature of the interaction of magnetism with convection on the surface. It stops the flow of convection in a very dense, dark sunspot, but then when it disperses across the surface, the little pieces of magnetism break up and they poke light pipes. It's like looking down slightly deeper into the sun, and it gets brighter. This is almost balanced in the sun. Now, the figure on the right, based upon an original idea by Erika Born-Vitenza, is just a very simple plot. You take the rotation period that you think you know, and you take the cycle period. If you've got 50, 60 years of data, which we do have for many stars as a result of Olin Wilson's effort at Mount Wilson Observatory, and you make a plot. And what you find is active stars go along here. In other words, they have many, for a given rotation period, they have a long cycle period. For a given rotation period, the weakly active stars lie down here, and the sun happens to lie sort of in between, which, as asked, the question was asked by Metcalfe et al. As to whether this was then a dynamo in transition. And this might neatly be tied together in a conceptual way by imagining that as the stars evolve along this branch here, the moderately old stars, and they move along this branch here, the moderately young stars of solar type, what's going on is that at this point, somewhere in here, the magnetic dipole moment sort of is starting to be decay in time. This is the sort of idea. Okay, and what that would do is it would stop the spin down because the magnetic fields don't reach as far out, because they're quadrupole and octopole, etc. And so this brings together a picture of the evolution from young to old sun-like stars. This remains to be confirmed or rejected. So, if you want to know more about this, I point you to a recent publication, actually of mine, in the very short introduction series of Oxford University Press. If you're interested, I wouldn't put this forward if it weren't relatively cheap. And so, this is a place that you might find some interesting reading along these lines. This is the end of the discussion today. I want to finish by just thanking you for listening, and I really appreciate the opportunity to speak to you all. There's much physics behind all this that I haven't been able to discuss. I've just basically given you a kind of a narrative of what the sun's history might be and its future evolution. Again, the real surprise is the magnetism. This is what solar physics is about.